There we go. Okay. Does anybody recognize this song? Nobody recognizes it? Okay. Okay. Believe it or not, here's the solo. Believe it or not, it's a play on the old-fashioned song. My hat, it has three corners. Three corners have my hat. So I know everybody knows that, right? Okay. So, and it's done by the famous trumpeter Wynton Marsalis. All right. Now, raise your hand if you've ever been in a room and no matter how loud the presenter talks or the person talks, it's like either you can't hear it or it sounds distorted. Okay? I can tell you one place that I can't stand on campus is when they have events inside of the Cage basketball arena. You know the arena? It's like, oh my God. Okay, stop talking. Okay. But anyway, believe it or not, those properties come from right angles. And what I'll do is that I'll explain a few concepts about sound and then apply those to mathematics. All right, so of course the title is Auditoriums and Concert Halls. What do their angles mean? All right, a little bit about sound. All right, as sound travels from a point of origin, it typically does one of three things. It reflects, absorbs, or diffuses. All right? Now, when the sound, whether or not it diffuses, absorbs, or reflects, depends on what material it deals with. Of course, in this room, right now, I can tell you it's a whole lot of reflecting doing because these are all solid walls and stuff. But inside of an auditorium or a concert hall, one of the things that absorbs sound is the seats, believe it or not. And those are the seats at Atlanta Symphony Hall. And then can you guess what other major factor actually absorbs sound? Can anybody take a guess? Exactly, the audience. Believe it or not, your body absorbs sound. That's weird, but it's true. All right. And with other special material, then you get the property of diffusion, which means that when the sound hits it, it splits it and divides the sound waves into different angles. All right, angles. The perfect angle of hearing is a 90-degree angle, okay, or AKA right next to you. So I'd like you to take a second. I want one partner to face forward and I want the other partner to turn towards the person. And what I want you to do, is that I want you to talk to that person in the lowest voice you possibly can. So go ahead and try it. Go ahead and try it.
You gonna face forward?
Okay.
Whisper or low voice? Whisper or low voice?
Say it again.
A whisper or low voice?
Oh, whisper voice. Now, if you notice while you're talking to that person, you can somewhat make out what they're saying and stuff. That's that perfect angle of hearing. Now, what I want you to do is try the same thing except both partners face forward. Both partners face forward. Now, notice it's even harder to sort of hear them. Don't you agree? All right, that's because that is that 90-degree angle of perfect hearing. All right. Now, the reason why headphones and stuff are made the way that they're made, not because to make them ergonomical to the head or whatever, but believe it or not, the actual apparatus and stuff that produces the sound, they want that to be a 90-degree angle to the actual ear and stuff. Oh, excuse me, I lost my train of thought, so excuse me. Okay, so they want it to be a 90-degree angle to the ear. All right. Now, I actually took a little trip to Atlanta 2 weeks ago to see a band festival. And while I was there, I was like, this is a perfect time to work on my project. So, without Atlanta Symphony Hall people knowing, so I don't know if this is illegal or not, but I took a couple of photos when I was in there. So, I don't know if I'm going to get in trouble for this. Okay, but if you notice inside of Atlanta Symphony Hall here, you see nothing but 90-degree angles and stuff as you observe the architecture here. It's because as the sound travels, they want the sound to hit your ear at a 90-degree angle. That way you hear everything from the loud tuba section to the soft clarinet section, pianos, fortes, everything. I'm sorry, I'm talking music. Does anybody understand what I'm saying? Okay, AKA soft and loud. Okay, so you see 90-degree angles over throughout the whole Atlanta Symphony Hall. You even see 90-degree angles on the ceiling. Now that's interesting. The reason why you have 90-degree angles on the ceiling and stuff is because you have something what you call reverb, which is something that we don't want as musicians and stuff. So those 90-degree angles help cancel out those extra sound waves. All right, as you can still see, 90-degree angles, that's the balcony area and stuff. And now let's get to our home planet. For auditorium. Okay, now, I know this is going to be pasted on YouTube, but I hope none of the music professors see this. Okay, for auditoriums, acoustics are horrible. Okay? Absolutely horrible. Okay? But you'll never hear us say that, though. But if you can see here, I believe that's Dr. Carlisle. He's our professor of piano here. The reason why all of our performances take place on the front part of the auditorium is because inside of For Auditorium, here is the stage, and this is where the sound goes. It goes up to these 90-degree angles. Somebody just tapped back in. I'm sorry if I disturbed y'all, please. Okay. So these 90-degree angles up here and stuff actually deflect and sit up there and cancel each other out, thus for not making it very efficient at hearing. But unlike in Atlanta Symphony Hall, this is Atlanta Symphony Hall, this 90-degree angle has a hypotenuse and stuff that actually extends some length of the top. I don't know the quite measurements of the Atlanta Symphony Hall, but you know, it sits up there, bounce, deflects, and then sends it out to the other 90-degree angles. All right, now everyone in the music department knows that we need a new auditorium. Okay, so I took the liberty of making a rough design of a new auditorium, which I bring this. Now, I'm not an artist and I'm not an art major or anything, so you gotta excuse the real simplicity, okay? But basically, I chose to keep the concept of 90-degree angles and their actual lengths and their lengths of their legs and their hypotenuse to determine some shape, form, or fashion of a really good auditorium. So the first thing that I chose to do was the perfector on the top, which is an example of Atlanta Symphony Hall. With that 90-degree angle and its hypotenuse, that the sound would sit up there and travel up, but then bounce forward. And then also I chose to keep with 90-degree angles and stuff along here and stuff is to also help with the perfect angle of hearing. All right. Now, one thing that I chose to do is that I chose not to put the angles on the walls and the ceiling. I thought that maybe, you know, it was a little bit crazy, and plus it was sort of hard to do that with that kind of stuff. So, all right, now let's do a couple of calculations with these right angles and stuff here, and you guys can help me along. Is there a duration? Okay. All right. All right, now let's see. We have a 90-degree angle, and it says that the first leg is 2.75, and the next leg is 1 inch. And you gotta excuse me if the model is not drawn to scale. So let's go ahead and solve that really quickly. The best way we can solve it is with the Pythagorean theorem, which of course is a squared plus b squared equals c squared. Everybody recognize that? Yeah, everybody recognizes it. All right, so A and B representing the legs, C representing the hypotenuse, which this is what we're trying to find here, or the angle, or AKA the angle of the overhang reflector. That's the one we're going to solve. Oh, oops, I used the wrong numbers. I'm sorry. So it was 1 inch and 1.25. Okay, all right. So we're trying to find the angle of the reflector. So let's go ahead and solve that. Let's plug in. We have 1 squared plus 1.25 squared equals c squared. We're trying to find c. Okay, 1 squared, of course, is what? 1. Then we have to sit up here and do the calculations. 1.25 squared is 1.5625. Right now, we're going to keep all of the decimals or whatever to make it a little bit more accurate, and then we'll round off a little bit later. All right, then you have C squared, then of course you combine this. That gives you 2.5625 equals C squared. Then you want to square both sides, which then gives you C equals the square root, okay. Which then gives us 1.600781059, a long number. Okay, so then we'll just round that to 1.6. So the length of the hypotenuse, or AKA the overhead reflector, would be 1.6 inches scale model. All right? And then, I don't think I need to solve the other one, because everybody gets the gist of it, don't you? Okay. All right. So that's about it. Do I have any questions? Does anyone have any questions? Yes.
Have you actually showed the music department your design, and are they going to take it into consideration?
Yes.
Do they like it?
Really? I talked to Dr. Pethel and stuff about it, because you know, it's no big secret around the music department that the auditorium is not so good. But you know, of course we have other things such as money and all that other kind of busy stuff that's involved. But you know, I did show it to him, and you know, he was like, "Oh, that's interesting." So,
they should name it after you.
Of course. We were on a trip in Athens. A funny story. We were on a trip in Athens, and we were, you know, all talking about the auditorium and everything. And then we sat up there and said, you know, if we were to build an auditorium, then you know, who would we name it after and all that kind of stuff. Then we came to the conclusion that it would be called the Dr. Carlisle Center of Music. And then, you know, because he's like the piano teacher and he does everything. And then we said that it would be called Pruitt Concert Hall. So, yeah, my name also. So, yep.
I got it.
Any other questions? Yes.
Just from a musical standpoint, when you go to build something like this, do you look for maximum reflection, or do you plan in a certain amount of diffusion and
I actually read about that, and you know, when you sit up there and you plan an auditorium, you actually plan for the maximum angle of diffusion and stuff, because believe it or not, when sound travels, this is actually sound traveling in front of you, but sound actually travels and creates a circle around you, believe it or not. I can't remember the name of the property because I can't remember what thing I read in that book. But so you sit up there and you actually try to find the maximum angle of hearing, maximum angle of diffusion, maximum angle of reflection, maximum angle of reverb, and there's one more. Well, anyway, that's 4 out of 5, so that's good enough. So yeah, you actually try to find those properties and stuff. Yes.
So is reverb caused when there's a smaller angle or a larger?
Reverb happens. Anybody play racquetball here? Everybody plays racquetball, and you notice in the racquetball, inside the racquetball ring, you hear that whoop, and you know you can basically hear a pin drop inside of there. Reverb happens when sound waves are created and they spread, and there's no device or there's no angle to actually counteract them. So the sound keeps traveling, and that's what you hear. That's that sound that you hear.
You don't want that.
And you don't want that in an auditorium. And so imagine if you were listening to someone sing, oh, and then next thing you know, you're so you don't want that in an auditorium. You don't want that. So any other questions?
Well, since we're pretty much out of time, I just wanted to ask you a personal question.
Okay.
As far as music goes, what are you doing with?
What do I play? I'm the principal trombonist here at Berry College, and hopefully one day I'll be one of the professors at Berry College.
Okay.
So that's one of my life goals.
I believe it. That was really good.
You already know your stuff.
Thank you. All right, so that's it.